Hello, and welcome to this online lecture. My name is Patty Kokish, and today we're doing material from Online Math 136 for Week 10. We'll be covering three sections today, all from Chapter 5. So we're going to do 5.4, 5.5, and 5.6. So let's start with Section 5.4, which is about polynomial and rational inequalities. So the first thing that we want to learn how to do is to solve polynomial inequalities, which we actually have already done a little bit of, and then we're also going to solve some rational inequalities. So the first way that you can use to solve these polynomial inequalities is the same way that we solved the quadratic inequalities, which was using its graph. So if we want to solve the inequality x minus 2 squared times x plus 1 is less than 0, then what we need to do is we need to graph that function. So this is a good review of graphing from last week. Your x-intercepts are going to be at 2 and negative 1. The multiplicity for 2 is 2 because that's the power, and the multiplicity for negative 1 is 1. So we know that at 2, our graph is going to touch, because anytime you have an even multiplicity, your graph is going to touch. And then at negative 1, your graph is going to cross, because we have an odd multiplicity. The y-intercept is 4 because if we set x equal to 0, we have 0 minus 2 squared, which is going to give us 4, times 0 plus 1. So it's 4 times 1, which is just 4. So from there, we can sketch a little graph. The first thing that you always want to do is go ahead and plot any intercepts that you have. And then the next thing you want to think about is end behavior. So if you were to multiply this out, you don't actually want to multiply it, but the whole thing you're thinking about is what would happen if I actually did multiply this out. So what you'd find is you'd have an x squared from the first term, and you'd multiply that by an x, and so your leading term would be x cubed. And we know that x cubed actually goes down on the left and up on the right. If you see these little blue arrows that were just drawn, it looks something like this. So then if we use the multiplicity along with the end behavior, we can sketch a pretty nice graph. So you'll see it's going up on the right and down on the left, just like x cubed does. At 2, we're touching. We go through our y-intercept of 4, and then at negative 1, we actually cross. So this is the graph of a polynomial. So like I said, this is a good review of some other Chapter 5 stuff. But what we actually want to do is solve this inequality. So if you think about it, we want x minus 2 squared times x plus 1 to be less than 0. So if we're talking about less than 0, it means we're talking below our x-axis. So if we're looking at that, it's going to be this red shaded part right here. And whenever we're giving answers, we're always giving our answers in terms of x. So we know that x has to be less than negative 1. There are two ways to write this. There's set builder notation, which reads x such that x is less than negative 1, or interval notation, which would go all the way from negative infinity up to negative 1. We have a parenthesis because negative 1 is not actually included. Okay, so let's learn a different way to solve polynomial inequalities. This way, you don't have to actually graph it. So the graphing is good practice because you've done a lot of graphing with polynomial and rational functions now. But I think that the easier way to do this, it's a little more straightforward and methodical, would be solving it algebraically. So let's say we want to solve this inequality x to the fourth is greater than x. And then we want to graph the solution set just on a number line, not on a two-dimensional plane. So step 1 for these is to always write your inequality so that you have something on the left, but you just have 0 on the right. So what we want to do is subtract x from both sides. So if we do that, we get x to the fourth minus x is greater than 0. And then step 2 is to determine the real zeros. Those are our x-intercepts. So all we really need to do is just factor. And in this case, it's a common factor problem, so we can take an x out of both of those things. So we have x times x cubed minus 1. Now, if you remember, this is actually the difference of two cubes. And that factor is like this. So we really have this x times x minus 1 times x squared plus x plus 1. So our real zeros are going to be 0, that's from this part right here, and 1. And that's from this part right here. This x squared plus x plus 1, if you do quadratic formula, what you'll end up with is a negative under your square root. So we don't have any real zeros from that one. So we just have 0 and 1. So at this point, what you need to do is you need to use those zeros that you found in step 2, and then go ahead and divide a number line into intervals. So what we're going to do is we're going to take a number line, basically from negative infinity up to infinity, put our lines at 0 and 1, and then write our intervals. So it's going to be negative infinity up to 0, and then we have a piece from 0 to 1, and then a piece from 1 to infinity. So then what we do is we actually just pick any number that we want in that interval and evaluate f at the number. All we care about is whether f is positive or negative. What it really means is that if f is positive, then all values in the interval are positive. But if f is negative, then all values of f in the interval are going to be negative. So if we look at this right here, these are intervals that we chose from negative infinity. Well, we didn't choose them. We wound up with our important points being at 0, 1. So then we created our number line and our intervals, negative infinity to 0, 0 to 1, and 1 to infinity. And then all we have to do is pick a number in each of these intervals. So a nice number is always what you want to choose. You don't want to make your life more difficult. So if you think about it, the nicest number that's going to be from negative infinity to 0 would probably be negative 1. The nicest number between 0 and 1, unfortunately, we're kind of stuck with a fraction here, but you could pick 1/2. That's not too bad. And then from 1 to infinity, 2 is a pretty nice number. So all we need to do is we need to go back to our equation where we just had everything on one side and 0 on the other, and we need to actually go ahead and figure out what x to the 4th minus x is. So if you take negative 1 and you plug it in there, what you're going to get is 2, which is a positive number. If you take 1/2 and you plug it in, you get negative 7 over 16. It's not very nice, and that's definitely negative. And then at 2, if you plug that in, you actually get 14, which is also positive. So since we want to know where f of x is positive because we have a greater than sign, what we do is we look for any of the positive pieces. So if you look here, we have a positive piece from negative infinity to 0, so that's part of our solution down here. And then we also have a positive piece from 1 to infinity, so that's also part of our solution. We do not include the negative because we only want the values where f of x is greater than 0. If we wanted f of x is less than 0, then we would have just taken this negative piece. And then if we wanted to graph the solution set, if you look at your number line, we have parentheses, not brackets, because 0 and 1 are not included. And then we are shading to the left of 0 and to the right of 1. The only part that's excluded is from 0 to 1. The other thing that I want to point out here is that this is your interval notation from negative infinity to 0, union 1 to infinity, or you can write it like this. This is the set builder notation again. So you can write it as x such that x is less than 0 or x is greater than 1. Either way is fine. You just have to pay attention to what MyMathLab wants. Okay, so for solving rational inequalities, we're going to go about pretty much the same two methods. We're going to use a graphing method, and then we're also going to do an algebraic method, which is pretty much the same thing as the polynomial method. So let's say we have x squared minus 4 over x squared minus 9 is greater than or equal to 0. And the first thing we want to do is to solve by graphing. So if you remember back, again, this is very good practice with previous chapter 5 stuff. So if you think about graphing, there are a few things we need to figure out. Probably the first thing would be to find your intercepts. And if you set your numerator equal to 0, that's going to help you find your x-intercepts. So if you set x squared minus 4 equal to 0, you're going to get two x-intercepts, negative 2 and positive 2. If you want to find your y-intercept, you always set x equal to 0. So if you do that, if you set both of these equal to 0, you just get negative 4 over negative 9, which is actually positive 4/9. So those are our intercepts there. We would also like to find our asymptotes. To find our vertical asymptotes, we set our denominator equal to 0 after we've canceled anything, which in this case we cannot. So if we set x squared minus 9 equal to 0, we get two asymptotes, one at x equals negative 3 and one at x equals positive 3. So we want to go ahead and draw those with some dotted lines. And we can see we're going to have some kind of a nice little shape there. Horizontal asymptote we also want to find. That's the one where you look at the degree of the numerator and the degree of the denominator. So the degree of the numerator is 2, degree of denominator is also 2. So in that case, it's going to be y equals our first coefficients divided by one another. So in this case, it's y equals 1 divided by 1, which is just 1. So we have a horizontal asymptote there. So you'd have to pick a few more points in order to see what's actually happening, but if you do that, you end up with this nice graph here where we have kind of these curvy pieces on the outside and then this parabola-looking thing in the middle. So in order to actually solve our inequality, what we wanted is we wanted our function to be greater than or equal to 0. So if we look on our graph, we want to be above the x-axis. So that's all these highlighted green pieces. So if we're writing this, there are two different ways, again, that we can write this. First is set builder notation. So we can say x such that x is less than -3, which would be this green piece over here, or x is between -2 and 2. And this time our numbers are included because we want greater than or equal to 0. So 0 is actually included. And then over here, we have x is greater than 3, so that's going to be this piece on the right. In addition, we can write this in interval notation. That would be from -infinity to -3, union -2 to 2, that has brackets because those two numbers are included, and then union 3 to infinity. You'll notice we do not include our 3 or our -3. They do not make our equation 0, so they're not included. The other thing is, if you actually take -3 or 3 and plug them in, those are the two values that make our denominator 0, which is something that we absolutely do not want to have happen. So we only include -2 and 2 because they make our entire function equal to 0. Okay, so now let's look at another way of doing this. Let's say we want to solve a rational inequality algebraically this time. So instead of having to graph this, what we want to do is we want to use kind of that same method that we did before where we had like a number line that we divide and pick test points. So if you'll notice, just like before, we always wanted to write it so that we have 0 on one side. So if you look at this one, we kind of have this 3 hanging out on the right. We definitely would like to get rid of that. So in order to get rid of that, you can subtract 3 from both sides. And what we have is we have 4x plus 5 over x plus 2, and then minus 3. Now the problem with this is that you need to just have one fraction on your left-hand side. So what we need to do is actually we need to get a common denominator, which would be x plus 2. So in order to not change our function, we multiply by x plus 2 over x plus 2, which is just a form of 1. So we multiply our -3 by that, and we go ahead and distribute -3 to the numerator. So we have 4x plus 5, that's from our first fraction, minus 3x minus 6. So that's what we get if we take our -3 and distribute it to both of these. And then x plus 2 is our denominator. We can go ahead and combine some like terms, and we're actually left with something very nice. X minus 1 in our numerator over x plus 2 is greater than or equal to 0. This is actually, I think, the hardest part of this problem. Okay, step 2 is to determine the real zeros and the numbers for which f is undefined. So really what you need to do is you need to set your numerator equal to 0, and you need to set your denominator equal to 0, and then those are the numbers that you're going to use to divide your number line. So the numerator is 0 when our x is equal to 1, right? Because if we put 1 in for x, we get 1 minus 1, which is 0. It's also undefined when our denominator is 0. So if you plug in x equals -2, you get -2 plus 2 in the denominator. That is also 0, so that one's going to be undefined. So what we need to do is we need to take our real zeros of our numerator and our denominator, which are those two numbers that we just found, and then we need to set up a number line. So if you think about it, we're going to have values from -infinity to -2. That's going to be our first piece. Then we're going to have a piece in the middle from -2 to 1, and then also a piece from 1 to infinity. So if we go ahead and draw a picture of this, we have -infinity to infinity. We have our two important numbers, -2 and 1. And then we just plug them back into our equation. You always want to plug them into the equation that had a 0 on the right-hand side. So if we plug -3 in, we actually get 4 out, which we know is positive. A nice number between -2 and 1 is 0. You always want to pick 0 anytime you can. One thing I want to note is that you can never pick the actual points that you put on your number line. So we cannot pick -2 and we cannot pick 1. And if we do that, we actually get -1/2, which is obviously a negative number. And then we have an interval from 1 to infinity. A nice number that lives in that interval would be 2. So if we take 2 and we plug it into our equation on the previous slide, we get 1/4, which is positive. Now, if you recall, what we want in this case is the positive answers. So all we do is we just look for positive, and we have a piece from this should be a negative infinity. Sorry, this is a little screwed up here. So this should be negative infinity to negative 2, and then we also have a positive piece from 1 to infinity. Now, the thing you need to keep in mind here is that we have greater than or equal to 0. Now, if you recall, we cannot include negative 2 because it makes our denominator 0, which is not good. But we can include 1 because that just makes our numerator equal to 0, which in turn makes our entire fraction equal to 0. So we actually do want to include 1, that's why there's a parenthesis there, but we don't want to include negative 2 because it makes our function undefined. And again, an additional way to write this would be the set builder notation, which is x such that x is less than negative 2 or x is greater than or equal to 1. And here's a nice little graph. You'll see at negative 2 there's a parenthesis because we do not want to include negative 2 since it makes our denominator 0. And we have a bracket at 1 because it makes our function equal to 0. Okay, so here's a really nice little box that is taken directly from your textbook that has the steps. So you can solve polynomial and rational inequalities algebraically always. You can also always solve them by graphing, unless maybe they're too difficult to graph or something like that. But you should be able to graph any of the ones that you have. But I think it's a little easier to do it algebraically, and if you're a little bit sick of graphing at this point, then it's a great other solution. So the first step is to always rewrite your polynomial or rational expression so that you have 0 on the right-hand side. And then if you have a rational expression, you need to make sure that it's written as a single quotient, meaning a single fraction. And then step 2, what you do is you determine the real numbers for which your expression equals 0. And if you have a rational expression, you need to also find the values where it's undefined. So that's where we set the numerator and the denominator equal to 0. Step 3 is to take a number line and divide it into intervals using the numbers from step 2. And then step 4 is to pick a test point that lives in each of those intervals and then determine if the value is positive or negative when you substitute it back in. And then if you're looking for greater than or equal to 0, then you're going to take the positive pieces. If you're looking for less than or equal to 0, then you're going to take the negative pieces. It's really important that you pay attention to whether you have that equals to part in your inequality, because that is going to change your inequality your solution set a little bit. It kind of helps you decide if you should include or exclude those actual numbers. But please remember to never include numbers that make your denominator 0 if you have a rational expression. Okay, let's move on to section 5.5. This one talks about the real zeros of a polynomial function. So the first thing we want to do is use something called the remainder and the factor theorems. And these are actually pretty nice. So I'm going to state them first, and then we're going to do some examples. So for remainder theorem, if f is a polynomial function, if f of x is divided by x minus c, then the remainder is f of c. So essentially, let's figure out what would happen if we divided x plus 2 into x cubed plus 3x squared plus 2x minus 1. Now, I don't want you to actually do that. What we want to do is we want to figure out what would that remainder be. So we have x plus 2 here. So the 0 that goes with that is negative 2. So what we need to do is we need to find f of negative 2. So all we do is we take negative 2 and we plug it in everywhere that we see in x. So we have negative 2 cubed plus 3 times negative 2 squared plus 2 times negative 2 minus 1. And if we simplify all of that, we should get negative 1. So that means if you divided x cubed plus 3x squared plus 2x minus 1 by x plus 2, you would end up with something that has a remainder of negative 1. And then for this one right here, the 0 that goes with x minus 1 is going to be positive 1, because if we plug positive 1 in for x, we get 1 minus 1, which is 0. So what we do is we take f of 1. So we take 1 and we substitute it in everywhere we see an x. So we have 1 cubed plus 3 times 1 squared plus 2 times 1 minus 1. And if we do that, we get 5. So that means if you were to take x cubed plus 3x squared plus 2x minus 1 and divide it by x minus 1, you would get a remainder of 5. Okay, the factor theorem. So again, f is our polynomial function. It says if x minus c is a factor of f, then f of c equals 0. And it also works the other way around. So what that means is that if we end up with a remainder of 0, then it means that that is one of our factors. So there are these kind of two equivalent things here. It says if f of c equals 0, then x minus c is a factor. Or if x minus c is a factor, then f of c equals 0. So it works in both directions. So let's go ahead and use our factor theorem. So what we want to find out is we want to find out if x plus 1 is a factor of this negative 2x cubed minus x squared plus 4x plus 3. So what we do is we think about what is the 0 that goes with that. So if we take a negative 1 and we were to plug it in for x, we will be finding f of negative 1, so we'd have negative 2 times negative 1 cubed minus negative 1 squared plus 4 times negative 1 plus 3. And if we simplify that very carefully following order of operations, what you will get is 0. So that means that yes, x plus 1 is going to be a factor, since when we plug negative 1 in for x, we get 0 as the remainder. Now, if you don't get 0, then it means it's not a factor. So for this one, if we plug 1 in, because 1 would be this 0, because 1 minus 1 gives you 0. If we plug that in, we actually get 4. So the remainder is going to be 4. So that means that x minus 1 is not a factor. So if you get a remainder of 0, then it is going to be a factor. If you get anything else, then it's not a factor. Okay, there's also a theorem that tells you the number of real zeros. So what that basically says is that a polynomial function cannot have more real zeros than its degree. So what we're going to do now is use something called the rational zeros theorem in order to list all potential rational zeros. So this looks a little confusing, but it's not too difficult once you actually get into the math part of it. So what you do is you always make sure that your polynomial is written in descending power order, which it normally should be. And essentially what you do is you find all of the factors of your constant term, that's going to be your last term, and then you find all of the factors of your leading coefficient, this a to the n. And then what you do is you divide all of those numbers, and what you end up with is a list of possible rational zeros. So let's look at an example. It'll be a lot easier if we look at this. So let's say we want to list the potential rational zeros of f of x equals 3x cubed plus 8x squared minus 7x minus 12. So the first thing that we look at is factors of our constant term, and then we looked at factors of our leading coefficient, and then we divide them. So our constant term, that's going to be a negative 12. So if we think of that, our factors are going to be 12 and 1, 6 and 2, and 3 and 4. Now, we put pluses and minuses outside of any of those because you could have the negative or the positive version of any of those. So those are going to be the factors of your constant term. And then what you do is you look at the factors of your leading coefficient, which in this case, our leading coefficient is 3. The only factors of 3 are just 3 and 1. So these are all numbers that go nicely into this number right here. That's what it means to be a factor. So then what we do is we take our list of our factors of our constant, which we normally call P, and the list of the factors of the leading coefficient, which we typically call Q, and then we divide P by Q. So what we get if we do that, we kind of just work our way down. So 1 divided by 1 gives us 1, 2 divided by 1 gives us 2, 3 divided by 1 gives us 3, 4 divided by 1 gives us 4, 6 divided by 1 gives us 6, and 12 divided by 1 gives us 12. And then we have to go back through again using this 3. So we get 1 divided by 3, that's 1/3. 2 divided by 3 is 2/3. 3 divided by 3 is just 1, which is already listed, so we don't need to relist it. 4 divided by 3 gives you 4/3. 6 divided by 3 gives you 2, which is already listed, so you don't have to relist it. And 12 divided by 3 gives you 4, which is also already listed. So essentially what this gives us is a complete list of possible rational zeros for this function right up here. Okay, now what we're going to do is we're going to put some of this stuff together and we're going to try to find the real zeros of our polynomial function. So what we want to do is we want to take that same polynomial function that we had, 3x cubed plus 8x squared minus 7x minus 12, and we'd like to write it in factored form. But it's not kind of a typical factoring problem because we don't really see anything that we can take out of everything, and we have this cube which is kind of causing an issue. So what we want to do is we want to try to find one of our real zeros. So step 1 is to use the degree of the polynomial to determine the maximum number of zeros. So in this case, our degree of our polynomial is 3 because we have an x cubed. So since f is a polynomial of degree 3, there are at most 3 real zeros. Step 2 is to go ahead and use the rational zeros theorem, which is the one that we just talked about. This can only be used if we have integer coefficients, which in our cases we do. And then what we do is we're going to use our rational zeros theorem along with our factor theorem to determine if we have any nice rational zeros. If we do, then we use something called either synthetic division or long division, which you should already be familiar with, in order to factor. And then we go ahead and repeat step 2 until we've found all of our zeros. So this is the complete list that we had already found, which is plus and minus 1, 2, 3, 4, 6, and 12, 1/3, 2/3, and 4/3. So now what we need to do is we need to kind of work our way through and test some of these. So the first thing you would do, I would normally start at the beginning with the nicest numbers, which would be like plus and minus 1, plus and minus 2. So they've already done this for us. And if you take -1, and you substitute it in, you're going to have 3 times -1 to the third power plus 8 times -1 squared minus 7 times -1 minus 12. And if we do all of that, we should get 0. So we know that -1 is a factor. So in order to figure out how it factors out, we do something called synthetic division. So you can also do long division. There's nothing wrong with that. But synthetic division is a little easier. So what we do is we take our -1 and we put it out front, and then we put our coefficients under our little symbol that we have here for division. And we have a 3, so we put a 3 here. We have an 8, so we put an 8 here, a -7, and a -12. So we put those all the way across. And then the first step in synthetic division is to take this first number, which in our case is a 3, and just drag it straight down and put it right below here. And then what you do is you kind of do multiplication, adding, sort of oscillates between those two things. So first thing we do is 3 times -1, that gives us -3. 8 plus -3 gives us 5. Okay, so what we did is we took our 3, we dragged it down, that's always the first step, and then we multiply, and then we add. And then we're going to multiply again, so we do 5 times -1, that gives us -5. -7 plus -5 gives us -12. So again, we multiplied and we added. Now we do it one more time. So you have -12 times -1, that gives us a +12. -12 plus +12 gives us 0. So we know that we have a remainder of 0. So if we want to factor this, it's going to factor as x plus 1. Okay, that would be our factor that goes with -1 for a 0. And then we're left with 3x squared plus 5x minus 12. Now, we should know how to factor that, so we can continue to factor kind of using our factor by grouping methods possibly, or guess and check, whatever you tend to like to do. And we end up with x plus 1 is one of our factors, x plus 3 is another factor, and 3x minus 4. Because 3x squared plus 5x minus 12 is going to factor into x plus 3 times 3x minus 4. So if we want the actual solutions, what we would do is we'd set each of these equal to 0. So we'd get x equals -1 from this one, which we already knew, x equals -3 from this one, and x equals 4/3 from this one. And you'll also notice that they are all in our list, as they should be if they're a rational 0. Okay, so here is kind of a summary of the steps for finding real zeros. First thing you do is you use the degree to determine the maximum number of real zeros. It's always just going to be the degree of your polynomial. And then if the polynomial has integer coefficients, then you list all of the numbers that can be potential rational zeros. And then what you do is either use substitution, synthetic division, or long division to test each of the rational zeros. And then if you get a remainder of 0, what you do is you kind of just continue to do that until you end up with what they call a depressed equation, or something that's been factored completely, or something that you can use other factoring methods in order to factor, just like the last one. Okay, so let's do another one. Let's find the real zeros of 2x to the 4th plus 13x cubed plus 29x squared plus 27x plus 9. And after we're done with that, we want to actually write it in factored form. So we know that there are at most 4 real zeros because we have a degree of 4. It's always going to match. And then we're going to list our potentials. So if you think about it, we have factors of 9, which would be 1 and 9 and 3. And then we have factors of 2, which would just be 1 and 2. So if we kind of divide those things, we have 9 divided by, or sorry, we're going to have 9 divided by 1, which will give us 9, 9 divided by 2, which is going to give us 9 halves, and then we have 3 divided by 1, which gives us 3, 3 divided by 2, which gives us 3 halves, and then we have 1 divided by 1, which just gives us 1, and 1 divided by 2, which gives us 1 half. So those are our potential rational zeros there. And then what we want to do is we want to go ahead and test some of these. So again, like I said earlier, you normally want to start with the nice numbers, which would be like plus and minus 1. So they took -1 because they know what they're doing. So if you take -1 and you plug it in here, again, we put our coefficients under. So we do 2, 13, 29, 27, and 9. Now I'm going to walk through this synthetic division again. So you always take this first number, this 2, or whatever it is, and you drag it straight down and you write it down there. And then you multiply, add, multiply, add, multiply, add until you're done. So you do 2 times -1, that gives you -2. You put that number here. 13 plus -2 gives you 11. Now again, we multiply. 11 times -1 gives you -11, and then you add. 29 plus -11 gives you 18. Again, you multiply. 18 times -1 gives you -18. 27 plus -18 gives you 9. 9 times -1 gives you -9. 9 minus 9 gives you 0. So we got 0 as our remainder, so that means that x plus 1 is going to be a factor. And in order to figure out what this part is that's left over, you just look at these numbers that are left down here. And I don't think I explained this last time, but if we have an x to the 4th here, that means that this is going to be the coefficient for x cubed. So it's always 1 less, because if you think about it, if you're factoring out an x, you're only going to have x to the 3rd left. So we have 2x cubed plus 11x squared plus 18x plus 9. That was what's left right here. And then if we try -1 again, you're actually going to work with this new adjusted equation. So you're going to do 2x cubed plus 11x squared plus 18x plus 9. And so you use those under here. And if you try -1 again, you actually get something else where the remainder is 0. So what you find out is that x plus 1 is kind of a double factor because it happens twice. So you get -1 out 2 different times. So you have x plus 1 squared, and then what you're left with is, again, these coefficients down here, 2x squared plus 9x plus 9. And then that actually factors as x plus 3 times 2x plus 3. And that, again, you can either use factor by grouping, which is kind of the very methodical way, or you could do guess and check. Sometimes it's easy to see these. So this one factors as x plus 1 squared times x plus 3 times 2x plus 3. So if we want to find the zeros, you just set each piece equal to 0. So you get -1, -3, and -3 halves, which were, again, all in our list that we have right up here. Okay, let's say we want to solve polynomial equations. So let's say we have something like this, 2x to the 4th plus 13x cubed plus 29x squared plus 27x plus 9. And this is the one that we just did, so we already have factored it. So if you want to do that, all you do is you just set each piece equal to 0, just like we did before, and you get -1, -3 halves, and -3. So for this one, it's a little, the only real difference is that we're actually solving an equation, so I can have something like equals 0, and you can actually solve it just by finding each of the zeros. So you're using that rational zero theorem along with synthetic or long division. Okay, so there are a couple of theorems here. Every polynomial function with real coefficients can be uniquely factored into a product of linear factors and/or irreducible or prime quadratic factors. And then a polynomial function of odd degree has real coefficients, has at least one real zero. So if you have an odd degree, you have to have at least one real zero. We're also going to learn something called the theorem for bounds on zeros. So this looks a little confusing when you first look at it, but I think it'll make more sense once we actually do a problem. So -m is going to be less than or equal to any real zero of f, which is less than or equal to +m. And essentially what this says is that if f is a polynomial function whose leading coefficient is 1, so it can be written like this, where you have x to the n plus your next coefficient times x to the n minus 1, and so on until you have your constant term, m is going to be the bound on the real zeros. So essentially, in order to find that, what you do is you take the maximum between 1 and the absolute value of all of your coefficients added up, and then you take 1 plus the maximum of all of the coefficients added up. And essentially what it's going to be is the smaller of these two numbers. So let's look at an example here. So let's say we have f of x equals x to the fifth plus 3x cubed minus 9x squared plus 5. So the leading coefficient is 1. And essentially what we need to do is we need to look at the maximum of 1. This is always going to be a 1. And then basically just all of your coefficients added up, but the absolute values. So you have absolute value of 5 plus absolute value of 0. The reason that there's a 0 is because there's no x, okay? So it would just be plus 0x. And then the absolute value of negative 9, absolute value of 3, and again, absolute value of 0. And you ignore this first coefficient. So if you do that, what we have is the maximum between 1 and 17. That's what you get if you add 5, negative 9, and 3, but the absolute value of all of those. So we know that the maximum between 1 and 17 is going to be 17 since that's larger. And then what we do is we take 1 plus the maximum of all of our singular coefficients. So if we look at these, we have the maximum of absolute value of 5, absolute value of 0, absolute value of negative 9, 3, and 0. And obviously the maximum between these is going to be the largest number, which in our case is 9. And if you do 1 plus 9, you get 10. And then what you do is you compare these two values, the 17 and the 10, and you see which one is smaller. In our case, 10 is smaller, so that's going to be our bound. So what it really means is that every real zero that we find has to be between negative 10 and positive 10. All right, let's do another one. So for g of x, we have 4x to the fifth minus 2x cubed plus 2x squared plus 1. So the first thing we want to do is write g so that it's the product of constant times a polynomial whose leading coefficient is 1 by go ahead and factoring out our leading coefficient. So we need to factor out a 4. So if we do that, if we factor a 4 out of everything, we have 4 times x to the fifth minus 1/2 x cubed plus 1/2 x squared plus 1/4. So first thing we want to do is find the maximum between 1 and all of the absolute values of our coefficients added up. So in our case, we have 1/4, 1/2, and negative 1/2, absolute values of those. And if we add 1/2 and 1/2 gives us 1, plus 1/4, that gives us 5/4. So the maximum between 1 and 5/4 is just 5/4. And then what we do is we take 1 plus the maximum of all of our individual terms. So 1/4, 0, 1/2, negative 1/2. And the largest number there is going to be 1/2. 1 plus 1/2 gives us 3/2. And what we want to do is we want to take the smaller of the two numbers, which in our case is 5/4, because 5/4 is actually smaller than 3/2. So what that tells us is that every real zero lies between negative 5/4 and positive 5/4. And then we want to use something called the intermediate value theorem. So if f is a polynomial and a is less than b, if a is less than b, and if f of a and f of b are opposite signs, meaning that either one is positive, one is negative, then there is at least one real zero between a and b. So if you think about this, if this is our a right here, this is our b, and this is our f of b, and this is our f of a, we can see that f of b is positive and f of a is negative. So we know that somewhere in between these two things, we have to touch our x-axis. So we have to have a zero somewhere. So we know that we're going to have a continuous function because we're talking about polynomials. So we know that somewhere we have to cross our x-axis. So this is basically just a depiction of what our intermediate value theorem actually means. So in order to actually use intermediate value theorem, we have to do a little bit of kind of guessing and checking. So we want to first show something. So the first kind of question, it gives you the two values, and then you have to show. And then after that, we're going to actually try to locate a real zero. So we want to show that f of x equals x to the fifth minus x cubed minus 1 has a zero between 1 and 2. So in order to do that, what we need to do is we need to find f of 1. So we plug 1 in here. We get 1 to the 5th minus 1 third to the 3rd minus 1. And if you do that, you get negative 1. And we want to find f of 2. So we plug in 2 to the 5th minus 2 cubed minus 1. And we get 23 if you do that. So because f of 1 is less than 0, and f of 2 is actually greater than 0, this is going to follow the intermediate value theorem, which tells you that you are going to have at least one 0 between 1 and 2. Okay, so if you want to approximate the zeros, what you do is you first find two integers so that you have a 0 between them, and then you would divide your interval into 10 equal subintervals. Evaluate f at each of the endpoints, and then what you want to do is you want to find two values where intermediate value theorem applies again, so something where the signs are different. One's positive, one's negative. So let's look at an example here. X to the 5th minus x cubed minus 1, it's the same one. We know that f of 1 is going to be negative 1, and we know that f of, let's see, what was the other one we found? Sorry, hold on, let me back up here. F of 1 is negative 1 and f of 2 is 23. So we know we have something between 1 and 2. So what we do is we divide our interval into 10 subintervals. So we divide it into tenths, basically. So we have 1.0, 1.1, 1.2, 1.3. And what we actually find is that when we get to 1.2 and 1.3, we have a negative number, and then it flips to positive. So as soon as we hit something where we have a negative and then a positive, or a positive and then a negative, we know we're going to have a 0 between these two numbers. So we know we have something between 1.2 and 1.3. But if we'd like to be a little bit more precise, what we do is we look at 1.2 and 1.3, and then we divide that into intervals. So we have 1.20, 1.21, 1.22, 1.23, and 1.24. And we would continue to go, but it looks like once we do 1.23, we get a negative number. But if you hop to 1.24, you actually get a positive number. So we know that our real 0 has to be between 1.23 and 1.24. Now you could continue to do this kind of forever. You could do 1.230, 1.231, 1.232, and you could find another level of precision. What's shown down here is the actual 0 from a graphing calculator, and you'll see that it's 1.2365057. So you could do this to get your real 0, but it would take a really long time. And you would probably never get your exact value. Okay, last section talks about complex zeros and the fundamental theorem of algebra. So a variable in the complex number system is referred to as a complex variable. A complex polynomial function, f, of degree n, is in kind of the same form as just your normal polynomial function. But an minus 1, a1, and a0 are complex numbers. An cannot be 0, and n is a non-negative integer, and x is a complex variable. As before, an is called the leading coefficient, and a complex number r is called a complex 0 if f of r equals 0. And then for the fundamental theorem of algebra, what we say is that every complex polynomial function, f of x, of degree n greater than or equal to 1 has at least one complex 0. One more theorem. Every complex polynomial function, f of x, that is of degree n greater than or equal to 1 can be factored into n linear factors. They're not necessarily distinct, and they're of this form here. So basically you can just factor just like we would normally be able to, except an, r1, r2 are all complex numbers. So that is, every complex polynomial function of degree n is greater than or equal to 1 has exactly n complex zeros, some of which may go ahead and repeat. So we could have repeated zeros before, we can have them again. Now, a very useful theorem, and we're going to put all this together in just a minute, is the conjugate pairs theorem. And essentially what that tells you is that if r equals a plus bi is a 0 of f, so we know that a plus bi is a 0 of your function, then the complex conjugate, so r bar, is going to be a minus bi, that's also going to be a 0 of f. So essentially what you know is that if a complex number is a 0, then its conjugate is also a 0. So let's go ahead and use this. So let's say we have a polynomial of degree 5 whose coefficients are real numbers, and we have zeros -2, -3i, and 4 plus 2i. And what we want to do is we want to find those remaining two zeros. Now, all we have to do is use that conjugate pairs theorem. So if we know that -3i is a 0, then we also know that +3i is a 0 because that's the conjugate. And if we know 2 plus 4i is a 0, then we also know that 2 minus 4i is going to be a 0. Okay, now let's find a polynomial function that has some specified zeros. So what we want to do is we want to find a polynomial of degree 4 whose coefficients are real numbers, and the zeros are going to be 1, 1, and 4 plus I. Now you need to remember the conjugate pairs theorem that tells you that if 4 plus I is a 0, then 4 minus I is also a 0. So essentially what we need to do is we need to multiply our factors. So if we know that 1 is a 0, we know that x minus 1 is going to be a factor. It tells us 1 twice, so we're going to have two of those, x minus 1 and another x minus 1. And then we have x minus 4 plus I, and then we have x minus 4 minus I, which is its conjugate. So now what we need to do is multiply all of this out. It looks really, really ugly when we start, but it will look nicer. First thing you do is you just have x squared minus 2x plus 1. That's what you get if you FOIL out these two. And then you FOIL out these two and you have this big mess. But what you should notice is that a bunch of stuff, once you distribute and actually cancel, you're going to have a positive 4i and a negative 4i that cancel. You're going to have a positive ix and a negative ix. And then you have this minus I squared, which hopefully you remember I squared is -1. So this becomes a plus 1. So really what we're left with is a, which can be any real number, x squared minus 2x plus 1, and then that's multiplied by x squared minus 8x plus 17. And we can go ahead and multiply all that out. That you kind of have to use distributive property, combine a lot of stuff, and you get a times x to the 4th minus 10x cubed plus 34x squared minus 42x plus 17. A can be any real number. You can make it 1 or 2, whatever you'd like. 1 is always easiest. The third thing under is finding complex zeros of a polynomial function. So let's say we have something like this, x to the 4th plus 2x cubed plus x squared minus 8x minus 20. So the degree is 4, so we know that we're going to have 4 complex zeros. The potential rational zeros are going to be 1, 2, 4, 5, 10, and 20, because those are the factors of 20 divided by the factors of 1. If we test some of these, we're going to test 2 first. You could probably test 1 and -1 and they won't work, so we go on to 2. And again, you use synthetic division, so you put 1, 2, 1, -8, -20 down here. Carry this down, multiply, add, multiply, add, multiply, add, multiply, add, you get a remainder of 0. So we know that x minus 2 is going to be one of our factors, and what's left over is x cubed plus 4x squared plus 9x plus 10. And then we probably should try another rational zero. If we try -2 on our new function, so we try it on our x cubed plus 4x squared plus 9x plus 10, you get a remainder of 0 again. And so we're left with x minus 2 times x plus 2. Those are our two real zeros, or sorry, our two rational zeros. And then we're left with x squared plus 2x plus 5. That's from this right down here. And if we set that equal to 0, we know that x equals 2, x equals -2. Those are going to be the easy ones. And then we have x squared plus 2x plus 5 equals 0. We have to use quadratic. So if we go ahead and do that, we get opposite of 2 plus or minus 2 squared minus 4 times 1 times 5, square root of that, all over 2 times 1. So we get -2 plus or minus square root of 16 over 2, which is going to simplify. So -2 plus or minus 4i over 2. Everything is divisible by 2, so you get -1 plus or minus 2i. So we know that the complex zeros are going to be -2, +2, -1 plus 2i, and -1 minus 2i. So if we want to write out our factored out version of our equation, we have x minus 2 times x plus 2. Those are our two rational zeros and the factors that go along with them. And then we have x minus -1 plus 2i and x minus -1 minus 2i. So that would be the factored form of our function f of x. So that's it for this week. Let me see if anybody's logged on and has questions. It looks like a couple of people are logged on. If there are any questions, you can go ahead and type them and I'll be able to see them. So I'll give you guys just a minute in case you have any questions. All right, it doesn't look like anybody is typing anything. If you'd like to rewatch this lecture, I'm more than happy to send you a link to it. So you just have to let me know. You should have my email address because you should get a little survey within the next day asking how the webinar was. So you'll be able to email me, ask me any questions. You may have also gotten my email address when you signed up for the webinar. So if you have any questions on anything while you're doing stuff this week, feel free to just let me know. And I hope you have a great rest of your week.